As we look at hydrogen bonding, we are just going to our next level of strength of dipole-dipole attractions with specific elements and atoms that cause exceptionally strong attractions. So here we have two compounds similar to before, made of the same atoms, the same elements, the same molar mass, the same number of electrons, but bonded in different ways. So they're both this. If we want to list the IMFs present in each, they're molecules, so they have dispersion. There is a bond that is polar, C to O in both cases, so they do have dipole-dipole. When we look at compounds made out of carbon and hydrogen, if it's just carbon and hydrogen, that would be nonpolar. Whenever we add in a halogen or an oxygen or a sulfur, it will become polar. So just by looking at the formula, even without the pictures, we can know that they would have dipole-dipole. Only propanol would have hydrogen bonding because that white circle represents a hydrogen on this red circle of an oxygen. You have to have an O on the H and the H on the O to have hydrogen bonding when you have a pure substance like this. That hydrogen bonding, or the extra strongness of those dipoles, makes that boiling point significantly higher. So we see a noticeable difference there, and those molecules sticking to one another much more strongly. Here we have three molecules, acetylene, chloromethane, and hydrogen peroxide, asking which could hydrogen bond to themselves. So first, the hydrogen has to be on the oxygen, on the nitrogen, or on the fluorine. Here, it is carbon to oxygen. Here, it is carbon to fluorine with hydrogens not on those. So only the H2O2 could hydrogen bond to itself. It has to be the H on the O, the N, or the F within the molecule to have hydrogen bonding within a pure substance. But when I put this with water, water has hydrogens on oxygens. So those hydrogens are unusually positive, and those hydrogens could hydrogen bond to this oxygen. So these hydrogens right here would never be involved in hydrogen bonding. A hydrogen has to be on the N or F. But since hydrogen is on an O in water, that hydrogen could hydrogen bond to this oxygen. That hydrogen could hydrogen bond to this fluorine, or obviously H2O and H2O2 have O's on H's and H's on O's. So we would have it there. Coming back up here, propanol can hydrogen bond to itself. Ethyl methyl ether cannot. But that oxygen is a place where something like water or even propanol could hydrogen bond to. We could have this hydrogen attract to that oxygen, and that would be hydrogen bonding. None of these other hydrogens that are bonded to carbon, and any of these are capable of hydrogen bonding. But that hydrogen is, as well as this one. All of these, this importance of hydrogen bonding isn't just so that we can have another type of intermolecular force. They are unusually strong, and they give molecules capable of a lot of hydrogen bonding special properties. Propanol can hydrogen bond, but really only in one place. Water, every place on it can hydrogen bond to really any place on another water molecule. So water has an unusually high surface tension. It beads up really well, and our little water strider bugs can skittle, run across it, or you can even float a paper clip, which if we think about the density of those things, the steel that it's made of is much more dense than water. It's 6 to 8 times more dense. Water, compared to other molecules with the same number of electrons, has an unusually high melting and boiling point. Methane has the same number of electrons, that CH4, as water does, and it is a gas at room temperature, but water is a liquid and has to be heated up quite a bit before it boils. Water evaporates very slowly, resulting in a low vapor pressure, And because of the way it sticks to itself and to other things, it has strong capillary action. That is like the ability of it to go up maybe not up a straw, sorry, but up into a tree through the roots and up to the leaves and all of that. It sticks to itself and other things very well. And it is a good universal solvent. It dissolves other things very well because it is polar, and because it is so polar, it dissolves most polar things, and it dissolves strongly most ionic things more than most others do.